Okay, so
Okay, so
start
let's start
today's
today's
lecture. So now
lecture.
we are
So now we are in the
ninth week
ninth
of the
week
course
of the course
Fundamentals of Nano
Fundamentals
and
of
Quantum
Nano and
Photonics.
Quantum Photonics.
So
So
up to week
up to
8,
week
we
8,
all talked
we all
about
talked about
the
the
fundamentals of
fundamentals of
nanophotonics, like
nanophotonics like
electromagnetic waves, how
electromagnetic waves, how it behaves as
nanoparticles behave,
nanoparticles or bulk medium,
what is the effect
what
of
is the effect
size
of
of
size
nanoparticle on
of
dispersion
nanoparticle on
relation,
dispersion relation,
Lorentz model, Drude
Lorentz
model.
model, Drude model.
And in this week,
And
we
in this
are
week, we
entering
are entering
into the quantum
into the
photonics,
quantum
and we will
photonics
discuss
and
the
we'll discuss
basics
the
of
basics of
the quantum
the quantum
photonics.
photonics.
So, starting with you can
So,
see
starting with you
on
can
the
see
screen.
on the screen.
Yeah.
Yeah.
So you can see one
So, you
figure
can see one
on the
figure
screen:
on the
intensity
screen,
versus size.
intensity
So
versus size.
it has four
So,
portions.
it has four portions.
So
So,
initial days in
initial
the
days
classical
in the
optics,
classical optics,
we were dealing with
we
the
were dealing with the
nanophotonics. So in nanophotonics,
nanophotonics. So, in
so first we will talk about the classical optics. In case of classical optics,
case of classical
the
optics,
size of the optical
the size of
systems,
the optical systems,
so large optical
so large
systems
optical systems
and
and
high intensity
high intensity
and devices were
and devices were
bulky.
bulky.
Okay.
Okay.
So then in the
So
last few
then in the
decades,
last few decades,
we moved from
we
classical
moved
optics
from
to
classical optics to
nanophotonics,
nanophotonics,
where the
where
size of
the
the
size of the
devices,
device
so size of the
so size of
devices
the devices
shrink to
shrink to
nanoscale.
nanoscale.
But
But
still,
still,
nanophotonics deals
nanophotonics
with
deals
a
with
relatively strong
relatively
light
strong light
that is
that is
high intensity,
high intensity
but confined
but
in
confined in
small volume.
small volume.
So we talked about
So we talked about in the previous uh,
lectures
lectures
in
that in case of nanophotonics,
nanostructures, the light
nanostructures,
is
the
strongly
light is
confined
strongly confined
in the
in
smaller
the
volume.
smaller volume.
And then
And then in the
30
last
years,
30-40 years,
we moved
we
from
moved from
nanophotonics to
nanophotonics to quantum
optics.
optics.
So where
So where
it the quantum
the
optics
quantum
was
optics
focusing
was
on
focusing
low
on the low
intensity,
intensity
where we deal with
where we
just a
deal
few
with just a
photons,
few
but
photons, but
and this
and this
resin
resin
will allow us
will allow us
to study the
to
particle
study the
nature of
particle nature
light.
of light.
So in the
So in the
classical optics, we
classical
were
optics, we were
considering
considering
light is treated
light
as a
is treated as
wave.
a wave.
Light is
Light
considered
is
as a
considered as
particle,
a particle
which we say
which we
quantum.
say quantum.
Quanta of light
Quanta
is
of light is photon.
okay.
Okay.
And in this
And
case,
in this case,
we focuses
we
on
focuses on
we focus
we
on
focus on
low
low
intensity.
intensity light.
And the next
And the
era,
next era
the
is
future
the
is
future is
quantum
quantum
nanophotonics.
nanophotonics. So
Quantum
quantum
nanophotonics
nanophotonics
is a
is a
combination
combination of
small device
small
size
device size
plus
plus
low
low
intensity
intensity, that is
few photons
few photons resin.
that is low
That
intensity.
is low intensity.
So today we
So
will
today
talk
we will talk
about
about the quantum
nanophotonics.
nanophotonics.
So
So
we saw that
we saw that
classic
classical
in
optics.
case of
In
classical
case of
optics,
classical
light is
optics,
treated
light is
as
treated as a
a wave where
wave,
like
where
say
like that is say
electromagnetic wave where we
electromagnetic
will
wave,
have
where we will have the
amplitude as well as
amplitude
phase.
as well as phase.
And in case
And
of
in case
quantum
of
optics,
quantum
the
optics,
light is
the light is quantized,
the quanta
and the
of
quanta of
that
that
the quanta
the
of
quanta
light
of
is
light is
photons, which is
photons,
considered as
which
the
is considered as
quantized
the
packets of
quantized packets
energy,
of energy,
and the energy
and
of
the
the
energy
photon
of
is
the
given
photon is
by
given by
E equals to
E
h
equals
nu
to
or
h nu,
E
or
equals
E
to h
equals
cross
to h
omega.
cross omega.
So
So
how the origin
how the origin of
quanta
quanta
quantum started?
quantum started?
So
So
uh,
uh,
black body radiation.
black body radiation.
So black body
The black
radiation
body
is
radiation
where the
is
quantum
where the
idea
quantum
started.
idea started.
So black body
So
is
black body is that
it,
it,
that absorbs
that
all light
absorbs all
and
lights
emits
and
radiation
emits radiation
later.
when heated.
So
So
classical theory
classical
predicted
theory
that
predicted that
emitted energy
emitted energy
increases
increases
indefinitely at
indefinitely
shorter
at
wavelength
shorter wavelength, that leads us so
that leads to the
that leads to the
ultraviolet
ultraviolet
catastrophe,
catastrophe.
whereas
Whereas
experiment showed the
experiment
opposite.
showed the opposite.
That is,
That
emission
is,
decreases
emission
at the
decreases at
higher
the
frequencies
higher
or shorter
frequencies or
wavelength.
shorter wavelength.
So
So
you can see
you
this
can see
plot
this
is
plot is
wavelength versus
wavelength versus
power
radiated
density.
power density.
So
So
in this
in
case,
this case,
you can see that
you can see that
the visible
the
region
visible region is
from 300
from 300 nanometer
nanometers
to the 700 nanometer,
and at the
and at the
higher
higher
frequency,
frequency,
this is the
this is the
classical region.
classical region.
So
So
if you will
if you will
move to the
move
higher
to the higher
frequencies, you
frequences,
can see that
you
it
can
is
see that it
increasing
is increasing
continuously.
continuously.
So how can we
So
define
how
this?
can we define
In
this?
case of
In
black
case
body
of black
radiation,
body radiation,
total energy
total energy
is equals
is
to
equals to
density of
density
modes
of modes
into
into
average energy.
average energy per mode.
So what is the
So
density
what is the density of mode? Density of modes is given by omega square
by pi
by
square
pi square
c cube and
c cube, and
energy
average energy,
that is thermal
that
energy
is thermal energy, that is
in
kT
classical.
in the classical
In the
limit. So
classical
in the
you can
classical
see
limit, you can see that
that classical theory
classical
predicted
theory
that
predicted that
energy
emitted energy
is increasing
is increasing
at higher
continuously at
frequency.
higher frequency.
So
So
it was given
it was given by
rho
rho
omega t
omega t
is equals to
is equals to omega square by pi square c cube
h cross
h
omega
cross omega
kt minus 1.
kT minus
So
1.
Planck,
So Planck in
so
nine,
what
so what
did Planck
did
say?
Planck said?
So in
So
19,
in 1900,
Planck suggested
Planck
that
suggested that
the energy
the
emitted by
energy
black
emitted by
body is
black
not
body is not
continuous.
continuous.
Light is
Light
emitted
is
in
emitted in
discrete energy
discrete
packets,
energy packets.
that is in
That is
quanta
in
form,
quanta form,
and the
and
energy
the
per
energy
photon
per
is given
photon is given by
h nu.
h nu.
So
So
we have to
we have
define
to define
the average.
the average energy.
So earlier
So
it was like
earlier it was like
so with
kT. So with the
frequency
frequency increasing,
this was
this was
continuously total
continuously,
energy was
total energy
continuously
was
increasing.
continuously increases.
But because
But
of this
because of
average
this
energy
average
which is
energy,
given
which is
by
given by
h cross
h
omega
cross
upon
omega upon
exponential h cross
exponential
omega
h
by
cross
kt
omega by
minus
kT minus 1,
This is the
This is the
average energy
average energy
per mode,
per
and
mode
which
and
will
which will
reduce
reduce.
this
So
part.
this part,
This so
this
average
so
energy reduces at higher frequency. So by considering this
this
correctly
correctly
explain the
explain
black
the
body
black
spectrum.
body
So this is
spectrum. So
the
the
this is how the concept of the
this is
photon
how the
works.
concept of the photon birth,
It
and
was
it
experimentally
was
proved also
experimentally proved also
that the energy
that the
is
energy
not
is not
increasing
increasing
continuously at high
continuously at
frequency.
higher frequency, and then
We are getting
we are
this
getting
curve.
this curve.
So now,
So now,
how can we
how
measure
can we
the
measure the
light quantum?
light
That
quantum?
is, how can
That
we
is,
measure
how can we
that
measure
photon
that
flux?
photon flux?
So,
So,
if we want to
if we
study
want to
photons
study photons
experimentally,
experimentally, so
suppose
suppose
this is the light
this is the
beam.
light beam.
The light beam
The
is
light
coming,
beam is coming,
and after
and
that,
after that,
we have
we
this.
have this.
We can have
We
either
can have either
photomultiplier tube or
photomultiplier tube
avalanche
or avalanche
APD
photodiode,
or
APD or
PMT.
PMT.
So
So
this is our
this is our
detector,
detector,
and then we
and
have
then we have
the
counter.
okay. So the output will be with respect to time.
Output will be with respect to time.
So
So
so what is
so what
photon
is
flux?
photon
So if you
flux?
want
So
to
if you
study
want to
photons
study photons
experimentally, the
experimentally,
light will
a
incident
light will incident
on the
on the
photomultiplier 2 or
photomultiplier
APD,
2 or
then
APD, then one
single
single
photon
photon
then the
will,
electron
then the
hole pair
electron
will
hole pair
generate.
will
The
generate.
light will
The
interact
light will interact with the
with the
matter,
electron hole pair
electron
will
hole pair
generate.
will generate,
Then they got
then they
separated.
got separated.
One
One
photon
photon
will interact
will
with other.
interact with other.
This
So
way
in
it
this way, it
will be
will be
multiplied.
multiplied,
And then
and then
a number or
a
large
number
number
or
of
large
photons
number of
will
photons
generate
will
in
generate
such
in such
process in the same
process
way.
in the same way.
So now we
So
want
now we want
then a large number of
then
photons will go to
a
the
large number of
counter,
photons will go to
and
the
then we
counter,
will detect
and
how many
then we will
numbers of
detect
photons are
how
detected per
many
second.
numbers
That
of
is
photons are
given by the
detected per
photon
second.
flux,
That is
which is
given by the
equivalent
photon
to
flux, which
E
is
upon H,
equivalent to
that is
P upon h
power
nu, that
by
is
the
power
energy of the
by
photon.
the energy of the
So
photon.
phi is equals to
So
P by
phi
H.
is equals to P by
So
h
for
nu.
example,
So for
if we
example,
have the 620
if we have
nanometer,
the 620 nanometer,
if we have a
if we
laser,
have a laser,
if we have a laser
if
that
we
is
have a
emitting
laser
at
that is emitting at
620 nanometer wavelength,
620 nanometer wavelength,
for
so for
to find out
to
energy,
find
we
out
have the
energy, we
formula
have the formula,
that is
that is
1.24
1.24
upon 0.62.
upon zero point
That
0.62.
will give us the
That will give us the
2 electron volt
2 electron
approximate.
volt approximate. Okay.
And the power of
And
the
the
laser
power of
is
the laser is
1 milliwatt.
1 milliwatt.
So here if we want to
So
calculate
here we
phi,
want to
phi
calculate phi. So
will be
phi will be equal to
P by H
P
nu.
by h nu.
So that will be
So
equals
that
to
will be equals
3
to
into 10 raised to
3
power
into 10
15
raised to power
photons.
15 photons per second.
If
So
you have the
if you
power
have the
and you want
power
to
and you
calculate,
want to calculate,
uh,
uh,
P is
so
equals
P
to
is equals to
energy by
energy
time,
by time,
and energy is
and
given by
energy is given by number of photons
energy of
into energy of a single photon
and time.
and time.
So 1
So
millijoule
1
per second
millijoule per second
upon
upon
2 eV.
2 eV.
So suppose
So
if we
suppose
have
if we have
10
3
raised to
into 10
power
raised to power
15 photons
15
per second.
photons per
So
second.
what is this
So what
telling
is
us?
this telling us?
So the
So
detector
the
is
detector is
to
never
measure
going to
these
measure
large number
these
of
large number of
photons
photons
because
because
detector is not
detector is not measuring continuously.
so
So
the point
the
is
point is,
so I'm writing
so
note.
I'm writing note here.
The detector
The
is
detector is
not measuring
not measuring
instantaneously.
instantaneously.
Okay,
Okay,
because
because
so
so
detector
the
has
detector has
dead time.
dead time.
So what is dead time?
Right.
So that
So
the dead
that
time is
the dead time
defined
is
as
defined as
the time
the
period
time period
where if any
where if
photon
any
is
photon is
coming to the
coming to
detector,
the
it will
detector,
not
it
get
will
detected.
not get detected.
So this is the
So this
dead
is the
time.
dead time.
So suppose
So
if
suppose if
large
a
number of
large number of
photons,
photons,
so
so
okay, so
okay, so
because
because
since that time,
since dead time is there.
so photon
So photon
detectors, for example,
detectors, for
PMTs
example,
or avalanche
PMTs or avalanche
photodiodes, register
photodiodes, register
individual
individual
photons as
photons
electrical
as
pulses,
electrical pulses.
but
So,
detectors
but
have some
detectors
deadline.
have some
Suppose we
deadline.
have
Suppose we have
a dead
a
time of
dead
1
time of one
microsecond. What does it
microsecond.
mean?
What does it mean? So the
Its meaning
its
is
meaning is,
the
so the
maximum practical
maximum
count
practical
rate is
count rate is
count rate for the
counted for the for
detector
the
is 10
detector
raised to
is
power
10 raised
6
to
photon.
power 6 photon per second.
So now we
So
saw
now
that
we saw that
a 1
a
milliwatt
1
power
milliwatt
laser
power laser
is giving us
is
the
giving
3
us
into
the
10
3
raised to
into
power.
10
So
raised to
10
power. So
or
10 raised to
15
power
photons
15
per second.
photons per second
Very
is
high.
very high.
So now
So now if we
to
want to
calculate,
calculate,
if we want
if we
to
want
detect
to
the
detect the
maximum
maximum
count rate, it
count
should be
rate,
of
it
the
should
order
be
of
of the order of 10
6
raised to power
photons
6
per second.
photons per
So
second.
now
So
when is
now
it
when is
possible?
it possible?
It is
It is
possible
possible
only
only
if I am
if I am
decreasing the
decreasing
power
the
from 1
power from
milliwatt
1
to 1
milliwatt to
picowatt.
1 picowatt.
So
So
suppose suppose
suppose
laser power
laser
is
power is
1
1
picowatt.
picowatt.
So
So
1 picowatt will
1
the
picowatt
flux
will give you the flux is
3 into 10 raised to power
3
6
into 10
photons
raised to
per second.
power 6 photons per second.
So
So
from
from
here,
from here,
what is the
what is the
inference from this
inference from this
detector
detector
limitation?
limitation?
That to study
That
the
to
quantum
study the
effects,
quantum effects,
we need
we
a lower
need a
intensity
lower intensity
that is of the order
that
of
is of the
picowatt
order of
range,
picowatt range,
or
or
we can
we
use
can use
the pulse
the
laser.
pulse laser.
So that will
So that will
what will pulse
what will
laser do?
pulse laser do?
The pulse
The
laser
pulse laser
will
will
decrease the number of
decrease the number of
photons
photons
per pulse.
per pulse.
So now
So
there
now
are some
there are some
examples.
examples.
So
So
suppose we have
suppose we have
one electron
one
volt.
electron volt.
So suppose we
So
have
suppose we
photon
have photon
having energy
having energy
1 electron
1 electron volt,
and the laser
and the
power
laser power
is 1
is
nano.
1 nanowatt,
Then phi
then
is equal
phi is
to
equals to
10 raised to power
10 raised to
minus.
power minus 9.
So that will give
That will give
us the
us the
6.25
6.25
into
into
10 raised to power
10 raised to
9
power
photons
9
per second.
photons per second.
Okay.
Okay.
So
So,
so the detector
so the detector
is defined by
is
two main
defined by two main
properties,
properties,
or the quantum source
or the
is
quantum source
defined
is
by
defined
two
by
things.
two
One is
things.
the quantum
One is the quantum
efficiency,
efficiency.
which is
Which is
given by
given
eta,
by eta,
and the second
and
is
the second is
responsivity of the
responsivity
detector.
of the detector.
It is
It
given
is
by
given by
R is
R
equals
is
to
equals to
eta, that is the
eta,
quantum
that is the quantum
efficiency, and
efficiency,
phi,
and
which is the
phi, which
photon
is the
flux.
photon flux.
I'm writing that
I'm
phi
writing
is
that
equals
phi
to
is equals to
photon flux.
photon flux.
So now
So
if we
now,
have
if
a
we have the
continuous laser,
continuous laser,
and if we have
and if we have
the photon
the photon
energy is
energy
1
is 1
electron volt and the
electron volt and the
power is
laser
1
power is 1
nanowatt,
nanowatt,
the
then
photon
the
flux is
photon flux is
6.25 into 10 raised
6.25
to
into
power
10 raised to power
9 photons per
9
second.
photons per second.
And what
And
if we
what
have
if
the
we have
pulse
the
laser?
pulse laser?
So second example is
Example is
for a
for a
pulse laser, that
pulse
is,
laser. That is,
uh,
uh,
it should have a
it should
repetition
have a
rate, and
repetition rate, and
periodically
periodically
a laser pulse
a
will
laser
fall
pulse
on
will
the
fall on the
detector.
detector.
So suppose for a
So
pulse
suppose
laser,
for a pulse laser,
we have the
we
lambda
have the lambda is equals to
800
800 nanometer,
power is equal
power is
to 1
equals to
milliwatt,
1 milliwatt,
and the
and
repetition
the
rate is,
repetition rate is,
that is I'm
that is
defining
I'm
as
defining as rep rate,
to
is
100
equals to
megahertz.
100 megahertz.
So now,
So now,
so you can,
so
if
you
we
can,
have the
if we
lambda, we
have the
can
lambda,
find
we can
out
find out
the
the
energy
energy
of the
of
photon
the
EP, which
photon.
is equals
EPH
to
is equals to
1.24 by
1.24 by
point 0.8,
point
which is
0.8, which is
approximately
approximately
1.55 electron.
1.55 electron volt.
And how can we
And
define
how can we define
the P?
the P?
Like we want to
Like we want to
have energy
have energy
pulse.
pulse.
So P
So
is
P
given
is
by
given by
energy
energy
in the into
in
the
the into
rep
the
rate.
rep rate.
Okay.
Okay.
So energy
So
of
energy of
pulse be
pulse
given
will be given by
1 milliwatt
1 milliwatt
upon 10 raised to
upon
power
10
8.
raised to
That is
power 8.
100
That is
megahertz.
100 megahertz. That is the
Repetition rate, which is
repetition rate,
will
which
give
is will give you
10 raised to power
10 raised to
minus
power
11 joule.
minus 11 joule.
So now to define the
To find the
flux,
photon flux,
that is
that is
phi
phi
is equals to
is
10
equals
raised to
to
power
10 raised to power minus 11 joule upon
1.5
1.55 into 1.6
is equals to
is equals to
10 raised to power
10 raised to
7
power 7 to
power
10 raised to
8.
power 8.
So we can
So
say
we can
that
say that
in case of
in case
pulse
of the
laser,
pulse laser,
we are getting
we are getting
number of counts
number of
of the
counts
order
is
of
of the order of 10 raised to power
7 to 10 raised to
7 to 10
and
raised
we
to power
can
8, and we
detect
can
this.
detect this.
So now
So now
to
to
detect,
detect,
so
so
so up to
so
now
up to now
we saw that
we saw that,
like
like
we have the
we
photon
have the
flux
photon
of
flux of
6.25
6.25 into 10 raised to power 9 photons per second.
that is
That
in
is,
1
in
nanosecond
1 nanosecond,
6 photons
6
will
photons will
arrive,
arrive.
and the
And
distance
the
we can
distance,
find
you
out
can
the
find out the
distance
distance
light travel in
light
1
travel in 1 second
will be equal to
will be
that.
equal to the.
So on an
So
average,
on an
only a
average,
few
only a
photons
few
will
photons
occupy
will
a 30
occupy a
centimeter
30
beam
centimeter
segment at
beam
such
segment
low
at
power.
such low power.
So this
This
shows
shows
why quantum
why
optics is
quantum optics is
challenging,
challenging,
and we have
and
to
we have to
uh,
uh,
we have
we have
a
a
handful of
handful
photons
of
in space
photons
and
in
time.
space and time.
So we saw
So
that
we
the
saw that
classical
the
optics
classical
deal
optics
with
will deal
many
with
photons,
many photons,
and light is
and
considered
light is
as a wave.
considered as a wave.
In case of
In
quantum
case of
optics,
quantum
a
optics,
few
there will be
photons
few
and light is
photons, and
considered
light will be
as a
considered
particle.
as a particle.
And to study
And to
quantum
study
properties,
quantum
we
properties,
have to
we have to
reduce the
reduce the
light intensity
light
from
intensity
milliwatt to
from milliwatt
picowatt
to
range.
picowatt
We
range,
have
or
to
we
use the
have to
short
use the
pulses.
short pulses.
Next, we saw that the
Next, we saw that
detectors
the
are limited
detectors
by
are
the death
limited by the dead
the
time
quantum
and the quantum
efficiency,
efficiency,
and the black
and
body
the black
radiation
body radiation problem
led to the
led to
photon
the
concept.
photon concept.
So,
So,
what did we
what did
understand
we
is that
understand is that
so
so
quantum
quantum
photonics
photonics
means working
means
with the
working with the
extremely
extremely
faint light sources,
faint light sources, that is
intensity,
low
and
intensity sources,
highly
and
sensitive
highly sensitive
detectors,
detectors,
because only
because
then
only then
we can see
we can
the
see
photon
the
nature.
photon nature of light.
So
So
we
we
started
started
to
to
understand what is the
understand what is
photon
the
status.
photon statistics.
So
So
to
to
understand the photon
understand the photon
statistics within the
statistics
quantum
within the
prism, we
quantum
started
prism,
with
we
the low
started with the low
intensity beam
intensity beam,
so that the
so that
discrete
the
nature of
discrete nature
photons
of
becomes
photons becomes
important.
important.
And we took
And
the
we took the
example
example
like 1
like
nano.
1 nanowatt.
If we
If
have the
we
1
have the 1 nanowatt
2
at
electron
2 electron volt, it will give us the 3.1 into 10 raised
9
to power 9
photons per
photons
second,
per second.
and in
And
30
in a
centimeter
30
segment,
centimeter segment,
3 photons
3
on an
photons on
average.
an average.
But measurement
But measurement
snapshots can give
snapshots can give
1,
0,
5,
1, 5,
but that is
etc. But
because
that
of
is
the
because of the
randomness.
randomness.
So the
So
randomness
the
will come,
randomness will come,
and the
and
random
the
detection
random
times.
detection times.
So
So
photons will
photons
arrive
will arrive
randomly
randomly
and at
and
random
at
time.
random
So
times.
the
So
repeated
the
short
repeated
interval.
short interval,
So repeated
so
short
repeated
interval
short interval
measurements
measurements
reveal
will
there will be
reveal
some
there will be
fluctuation.
some fluctuations.
So
So
we divide the
we
beam
divide the beam segment into many
segments
subsegments
and find the
and find the
probability of
probability of finding
finding n
n
photons
photons
will follow a
will follow a
Poisson distribution
Poisson
which is
distribution,
given
which is
by
given by.
which is
Which is
given by
given by the
this
this
probability.
probability.
So here
So
this
here
n
this
bar is
n bar
equals
is
to
equals to
mean photon
mean
number.
photon number.
So Pn
So
is equals
Pn is
to
equals to
bar n
cup
bar
n
power
bar power n
exponential minus
exponential
n bar
minus n
upon
bar
n
upon
factorial.
n factorial.
So
So
various
there are
examples
various
where
examples
we
where
consider
we
that if
consider
n
that
bar
if
is
n
equals
bar is equals
to 2.1,
2.1,
so
so
substitute the value
substitute the value
and
and 0.1.
so mostly
So mostly
0
0
photons.
photons.
And if
And
r
if
is
n
equal
bar
to
is
1,
equals to 1,
so mostly
so
0
mostly
photons
zero
and
photons
sometimes
and
it's 1.
sometimes it 1.
So for n
So
bar,
for n bar, so we can,
so for
so for
n is
n is
bar
n bar
equals to
is
0,
equals to 0.1,
we are getting
we are
most,
getting most
0 photons
zero
mostly.
photons mostly,
In the
and
rare
it was
case,
a rare
we were
case when
getting
we were getting
uh,
uh,
the number of
the
photons
number of
is 1.
photon is 1.
For n is
For
equals to
n is
n
equals
bar
to
is
n
equal
bar
to
is
1,
equals to 1,
distribution falls as
distribution
1 by
falls as
e
1
by
by
2
e,
e
1
1
by
by
2 e,
6
1
like
by
this.
6 like this.
And for the
And
larger
for the larger n
bar,
bar,
so the
so the
distribution will widen.
distribution will
It will
widen
be
and it
centered
will be
at.
centered at the n bar.
So now
So
how
now
to
how to
define the
define the
fluctuations? So there
fluctuations?
are,
So there are,
so in case of
in case of volumetric distribution,
so here we
so
saw
here
that
we saw that
delta
this
n, delta n is
delta n is a
standard.
standard deviation.
So standard
So
deviation
standard deviation is equals to the
n bar root
n bar root,
and the
and the
absolute
absolute
fluctuations
fluctuations
will grow with
will grow with
intensity. So
intensity.
we saw in
So
the
we saw
previous
in the
cases,
previous cases,
we saw in the
we
previous cases
saw in
that
the previous
if
cases
we are,
that if
uh,
we are
if we have the higher
if we have the
intensity,
higher intensity,
if we have the
if
higher
we have the higher
intensity, then
intensity,
we are
then
having
we are having
uh,
uh,
a large
a large
fluctuations, as
fluctuations,
well as
as
there
well
will be
as there
large
will
number
be a
of
large number of
photons,
photons,
and in the
and
such
in the
case, a
such case
detector
a
will not
detector
be
will
able to
not be
detect
able
them.
to detect them.
But if we will
But
deal
if we
with
will
low
deal with the low
intensity,
intensity,
the
the
fluctuations will get
fluctuations will
reduced.
get reduced,
And also,
and also
the detector
the
will be
detector
able
will
to
be able to
detect.
detect.
How can we
How
define
can
the
we define the
relative
relative
fluctuations?
fluctuations?
So,
So
relative
the relative
fluctuations
fluctuations
is given by
is given
delta
by
n
delta n upon n bar.
delta n
Delta n we know that
n bar
n bar
the root
under root
n bar which
n bar,
is
which
1
is
by
1 by
n bar.
root n bar.
So
So
it tells
it
us as the
tells us as the
intensity will
intensity will
increase,
increase,
these relative
these relative
fluctuations
fluctuations
will
will
decrease.
decrease.
So at the
So
high
at the
power
high power
lasers,
lasers,
classical behavior.
classical
So
behavior. So
in that
in
case,
that
the
case, the
fluctuations will be
fluctiations will be
negligible because it is
negligible
over
because it is over
time
on the
average
time average,
and all
and
the
all the
uh,
uh,
and these are
and these are independent.
so that
So the
we don't care
we
about
don't care
the
about the
fluctuation.
fluctuations.
But when
But when
we talk
we
about the
talk about the
low
low
intensity weak
intensity or
beams,
weak beams,
at that
at
point
that point
fluctuations matter
fluctuations matter,
and we enter
and we
into the
enter into the quantum region.
so
So
suppose
suppose,
we
so
have an
we have
example
an
that
example that
argon laser
argon laser, which
at
at
540
540
nanometer
nanometer wavelength,
which has the
which
power
has
of
the
1
power of zero point
picowatt
0.1 picowatt,
and with
and with
20% quantum
20%
efficiency.
quantum
So
efficiency.
eta
So eta
is equals to
is equals to
20%
20%,
and
and
T is
t
equals
is
to 1
equals to zero point 0.1 second.
So now we
So
want to
now we
calculate
want to
the
calculate the
photon flux.
photon flux.
So which we
So
saw
which we
that the
saw
photon
that the
flux
photon flux
phi
phi
p by h,
p by h nu,
which will give us
which will
the
give us the
2.65
2.65 into 10 raised to power 5 photons per second.
So now we
So
saw
now we saw
that
that
our
10 raised to power 5 photons is in the
detector range
detector range,
because we are
because we
using
are
a
using
very
a
low
very low
intensity
intensity
laser
laser
that is of the order
that
of
is of the order of zero point 0.1 picowatt,
2.65.
2.65 photons per second.
So we can
So
find the
we can
detected
find the
counts
detected
also.
counts also.
Um,
Um,
that will be
that will be
5,300
5,300,
and the
and the
fluctuations.
fluctuations.
These
So
are
these are the
mean photon number.
mean photon number
N
count, that
bar.
is n bar.
We want
If
to
you
calculate
want
the
to calculate the
fluctuations. Delta
fluctuations
n
delta n, it will
n
n
bar under.
bar under root.
So
So
basically
basically
under root
under root
5,000,
5,300,
which will
which will
approximately give us
approximately
the
give us this
value of 70.
value of 70.
And the relative
And the relative
fluctuation that we
fluctuations
just
that we just calculated it,
delta n
delta
upon
n upon under root
5,300.
5,300.
So relative
So
fluctuation,
relative
I'm
fluctuation, I'm
representing this,
representing it is
I'm
I'm
representing it
representing it
fluctuation
relative
by
fluctuation is given by
delta n is 7
delta n is 70
and n bar
and
is
n bar is
5,300,
5,300,
which is
which is
approximately
approximately is
it
1.3%,
is
and it is
negligible.
negligible.
So now
So
how can
now
we
how
define
can we define
the
the
statistics of light?
statistics of light?
That
That
so there are
so
three
there are three
so
cases.
we
So
are define we
we are
can
define we
define
can
the
define
classical
the
light
classical
as well as
light
the
as well as the
quantum
quantum
light
light by the
seeing the
by seeing
photon.
the photon statistics.
So if
So
we have
if we
the
have the
Poissonian, if we have
if we
the
have the
Poissonian
Poissonian
statistics,
statistics, so
it is
it is
categorized into three
categorized into
parts.
three
One
parts.
is
So one is
Poissonian
Poissonian
statistics,
statistic,
other one is
other one is
sub-Poissonian,
sub-Poissonian,
and the last
and
and the third
the
one is
third one is
super-Poissonian.
super Poissonian.
So in
So
case of
in case
Poissonian
of Poissonian
statistics,
statistics, where
delta n is
delta n
equals
is
to
equals to,
that is the standard
that is the standard
is
deviation,
exactly
is
equal to
exactly
the
equal to the
square root of
square root
mean
of
value means mean value of
mean value
photons
of
per
photons
second.
per second.
It will give you
It will
a
give you a
coherent light.
coherent light.
Then
Then super
super-Poissonian case.
Poissonian case.
In this
In
case,
this case,
the standard
the
deviation
standard deviation delta n
is greater
is
than the
greater than the
square root of mean
square root
value
of
of
mean number of
photons.
photons,
And
and
so in this
so in
case,
this case,
the example
the
is
example is
light
thermal light,
where there is no
where there is no coherence, there is
relation
no correlation between
amplitude and
amplitude and
phase.
phase.
relation
There's no
between
relation between phase.
it follows the
It follows the
superpoisonian
superpoisonian
statistics.
statistics.
Then the last
Then the last is
subpoison
subpoison
in the
in the
case
case
where we
where
define
we
the
define the
quantum depth.
quantum light.
The
The
interesting part
interesting
is
part is
there is
there is
no
no
analogy of
analogy of
subpoisonian
subpoisonian
statistics in the
statistics in the
classical regime.
classical regime.
So the
So
motive
the
is not
motive
to
is
gain
not
the
to gain the
Poissonian
Poissonian
statistics to
statistics
get
to
the
get the
quantum nature.
quantum nature.
The aim is
The
to
aim
get
is to
the
get the
sub-Poissonian
sub-Poissonian
statistics where there
statistics where there
is no
is
analogy
no
of
analogy
classical
of
behavior
classical behavior
and only the
and only the
quantum nature of
quantum
light
nature of
exists.
light exists.
So the
So
quantum
the
light,
quantum light,
and in this
and
case,
in this case,
the standard
the standard
deviation
deviation
delta n
delta
is
n
lesser
is
than
lesser
square root
than
of
square
mean
root of
numbers of
mean numbers
photons
of
per
photons
second.
per second.
So in this
So in
case,
this case,
the
the
examples are
examples are
single
single
photons
photons
and
and
anti-bunching.
anti-bunching.
So now we
So
have
now
defined
we
the
have
photon
defined the photon
statistics,
statistics:
Poisson,
Poisson,
Poissonian,
Poissonian,
super
super
Poissonian,
Poissonian,
sub-Poissonian.
sub-Poissonian.
So on the
So
basis
on
of
the
that,
basis of
we
that,
can define
we
the
can
source
define the
and
source and
identify
identify
when we
when
really
we
have a
really have
quantum
a
light
quantum
source.
light source.
So just to
So
recap,
just to recap,
Poissonian
Poissonian delta n square
is equals to n
is
bar
equals to n bar
coherent light, and
coherent
this is the
light, and
case of
this is the
ideal
case of
laser.
ideal laser.
Super Poissonian,
Super
thermal and
Poissonian, thermal and
incoherent light, where
incoherent
we have
light,
the
where we have
broadband
the
and the
broadband and the
fluctuations will be there.
fluctuations will be there.
In case of
In case of
sub-Poissonian, there is no
subpoisonian, there is
classical
no
analog.
classical
It is
analog,
a
and it is
purely
a
a
purely
signature
a
of
signature of
quantum
quantum light.
single photon
Single
sources,
photon
grid
sources,
states,
squid
and
states, or anti-bunching.
so now
So now,
what
what
happens when
happens
we
when we
so
so
now
now
what
what
what is the
what is the
degradation of
degradation of
status of
status
photon?
of
So
photon?
here
So here,
we study that.
study that.
So up to
So
now
up to now,
we understood
we
the
understood
classical
the
and quantum
classical and
nature.
quantum
Then
nature. Then
how will we define the
define the
exact quantum
exact
nature on the
nature
basis
on
of
the
the
basis
photon
of the photon
statistics?
statistics.
Now, what
What
factors will
factors
affect
will
the
affect the
photon statistics,
photon
or what are the
statistics, or what are the
limitations for
limitations
observing
for
a
observing
quantum
a
nature of the
quantum nature
photon?
of the photon?
So,
So
next is this
next
is the
is this is the
degradation.
degradation.
Degradation of
Degradation of
statistics
statistics
due to
due
losses.
to law.
So,
So
suppose
suppose
100 numbers of
100 numbers
photons
of
are
photons
coming.
are coming.
Here I have
Here
a
I
lossy
have a
media,
lossy media,
and after
and
time
after
t,
time t,
this is a
this is a
detector.
detector.
Okay.
Okay.
So now
So
the
now
absorption
the
process
absorption
is
process is
completely random.
completely random.
So the
So the
statistics will
statistics
degrade,
will
and
degrade,
after
and after
transmission,
transmission.
so
So
earlier also
earlier also,
we studied
we
that
studied that
if the light
if the
is
light is
interacting with the
interacting
matter,
with the
and
matter, and
the
the
intensity will
intensity will
decay, like
decay, like
evanescent
evanescent
decays.
decay.
We have
We
already
have
studied
already studied the
evanescent decay,
evanescent decay,
exponential minus
exponential
alpha. So
minus alpha.
similarly,
So similarly,
if we have
if
a
we
hundred
have
number
a
of
hundred number of
photons,
photons,
so these are
so
your
these are your n in.
So how
So
many
how
number of
many number
photons
of
this
photon
detector
this
will detect
detector will
is
detect
defined by
is
n
defined
out.
by n out.
And
And
after
after
passing
passing
through a lossy
through a
media,
lossy media, the
transmission through a
transmission
medium
through a
is
medium
defined by
is defined by
and the number
and
of
the number of
photons
photons
we got at
we
the
got
detector
at the
is given
detector is
by
given
n
by
out is
n
equals
out
to
is
n
equals to n
input
input
exponential
exponential
minus
minus
alpha L.
alpha n.
So that is
So that is
100
100
exponential minus
exponential
alpha
minus
L.
alpha L.
So
So
the absorption
the
process
absorption
is
process
random
is
and
random
it
and it
degrades
degrades the
statistics,
statistics,
photon statistics.
photon statistics.
So in case of
So in case of
perfect
perfect
subpoisoning,
subpoisonia,
that is when
that
there are
is when
no
there are no
fluctuations
fluctuations
and the standard
and the
deviation
standard
is
deviation is
completely zero.
completely zero.
So this is
So this is
so
so for
for delta
for
n is
delta
equals to
n is
zero,
equals to zero,
perfect quantum
perfect
source.
quantum source.
So,
So,
but after
but after
providing a small
providing a
loss,
small loss,
then after
after
small loss,
small loss,
the
the
statistics are still
statistics are still
subpoisonian,
subpoisonian,
but the
but
delta
the
n will
delta
not be
n will
equals to
not be
zero.
equals
It
to
is
zero.
greater
It
than
is
zero,
greater than
and
zero,
it will
and it will if
it is in
if
the
it is in
range
the
of
range of it
zero
zero
delta n
delta n
and
and
bar.
n bar.
So in this
So
case,
in this
the
case,
statistics
the
is still
statistic is still
subpoisonian,
subpoisonia,
but not
but not
perfect
perfect
subpoisonian.
subpoisonia.
And in case of
And in case of
larger loss,
larger loss,
for a large
for a
amount of
large
loss,
amount of loss,
when the
when the
fluctuations are
fluctuations are
much larger than
much
the
larger
incident
than the
beam,
incident beam,
then it will
then
become
it will
eventually
become
it becomes
eventually it
super
become the
poison,
super poisonian,
where
where
incoherent
incoherent
sources
sources
and
and
so what is the
so what is the
conclusion? The
conclusion it? So the
conclusion is
conclusion is
the
the
conclusion is
conclusion is
optical loss
optical
degrades
loss
the photon
degrades the photon
statistics.
statistics.
So now how
So
can
now
we
how
model
can we model
this
this
the effect of
the effect of
loss in
loss
case of
in
by
case
using
of
the
by
optical
using the optical
components?
components?
So for
So
that
for
case,
that
we
case,
are
we are
modeling our
modeling
loss
our loss
using a beam
using a
splitter.
beam splitter.
So we are
So
using
we are using
we are
we
modeling
are modeling
the loss
the
by using the
loss
beam
by
splitter.
using the
That
beam
is,
splitter. That
our
is,
light is
our
coming,
light is coming,
and here we
and
have
here
beam
we have
splitter.
beam splitter.
So
So
one portion of
one
light is
portion of light is
transmitted,
transmitted,
and the one
and the
portion of
one
light is
portion of light
reflected.
is reflected.
So suppose
So
if
suppose
T
if
light
T
is
light is
transmitted,
transmitted,
one minus T
1
is
minus T is
reflected.
reflected.
So we can
So we
like
can
this we can
like this we
model
can
our
model
loss
our
by
loss
beam
by
splitter with
beam splitter with
transmission
transmission
coefficient T.
coefficient T.
So
So
fraction of
fraction of
light T is
light T is
transmitted and one
transmitted
minus
and
T
1
is
minus T
reflected.
is reflected.
So we can
So we can
use
use
this
this
in quantum
in
optics
quantum optics
calculations.
calculations.
So now
So
what
now what
happens when we
happens
try
when we try
to detect a
to
photon?
detect a photon?
So that is
So
photo
that is
detection.
photo detection.
Photo detection,
Photo detection,
short noise
short
estimate.
noise limit.
Okay.
Okay.
So
So
first of all,
first of all,
suppose we are
suppose we
having
are having
a
a
classical
classical
electromagnetic wave
electromagnetic wave
with a
with
constant
a constant
amplitude,
amplitude,
and
and
so if that EM wave is
Wave is
incidenting on a
incidental
detector.
on a
It means
detector.
we are
It means we are
depositing
depositing
some
some
energy
energy
into
into
photodetector,
photodetector,
and that
and
energy
that energy
will
will
generate the
generate
electrons
the
in hole
electrons in
pairs
hole pairs
that will give us
that will
the
give us the
photoelectrons,
photoelectrons,
photocurrent.
photocurrent.
So
So,
what is
what
happening
is
in this
happening in this
case? So we
case?
have
So, we have
electromagnetic field which
electromagnetic
is
field which is
incidenting.
incidenting,
Then it will
then it
interact
will interact
with the
with the
material,
material,
and it will
and it will
generate the
generate the
electron hole
electron
pairs,
hole pairs,
and then they will
and then they will
separate,
separate,
and
and
then it
then it
and then it
and
will
then
give
it will give
then it will
then
give
it will
the
give the
current, that
current,
is the
that is the
photodetection
photo
process.
detection
So
process.
the
So the
probability of
probability of
generating a
generating a
photoelectron in
photoelectron in
response to an
response to
incident
an
field is
incident
itself
field is itself
Poissonian.
Poissonian.
The
The
probability
probability of
generating
generating
probability of
probability of
generating a
generating a
photoelectron
photoelectron
in response
in
to an
response to
incident
an
field
incident field
is
is
itself
itself
Poissonian.
Poissonian.
So
So
for a
for
classical
a
wave
classical
of the
EM wave of
constant
the
amplitude,
constant amplitude,
the
the
probability of
probability of
generating
generating
photoelectrons
photoelectrons
at a particular
at a
time
particular
is
time
given
is given by
Pn
Pn
is equals to
is
n
equals to n
bar
bar
n
power n
exponential minus
exponential minus
n
n bar
upon n
upon
factorial.
n factorial.
So
So
this is
this is
P
this P is
representing the
representing by probability of
generating an
generating n
electrons.
electrons.
The probability
The
of
probability of generating n
electrons at a
electrons at
particular
a
time.
particular time.
So what
So what
is the
is
implication
the implication of this
statistics?
statistics?
Like if we're
Like if we're
considering the
considering a
classical EM
classical
also,
EM wave
then also
also,
we
then
are
also
getting
we are getting the
Poissonian
Poissonian
distribution.
distribution.
So
So
what does it
what
suggest
does it
that? It
suggest
suggests
that? It
that the
suggests that
observing
the
Poissonian
observing
counts
Poissonian counts
doesn't
doesn't
prove the
prove
quantum
the
nature,
quantum nature,
but
but
sub-Poissonian counts
sub-Poissonian
cannot
counts
come from
cannot come from
classical phase,
classical
and
phase,
it is
and it is
definitely a
definitely a
quantum signature.
quantum signature.
So
So
next,
now,
if we are
if we
observing,
are observing,
okay, so if we are
okay, so if
observing
we are
Poissonian
observing Poissonian
statistics, it doesn't
statistics,
mean
it
that our
doesn't mean
source
that
is
our source
quantum.
is quantum.
So if
So
observe the
if observe the
sub-Poissonian statistic,
sub-Poissonian
then
statistic,
quantum
then
phenomena,
quantum phenomena,
and
and
cannot
it
be
cannot be
explained by using
explained
photo
by
detection
using the
process.
photo detection process.
So first of all,
So
we will
first of
define
all, we
what
will
is
define what is
photocurrent.
photocurrent.
That is given by
That is given by I
is equals to
is
eta,
equals to
the
eta,
quantum
that is the quantum
efficiency,
efficiency,
eta E
E
into P upon
into P
cross
upon H
omega,
cross omega,
and
and
responsivity is
responsivity
equals to
is equals to
I by
I
P.
by P.
So where
So
P
where
is
P is
incident power
incident power
is
and I is the photocurrent.
which is given
which
by
is given by eta E
h cross.
upon h cross omega.
So now,
So now,
so here we
so
have,
here we have the
so now the
so
noise
now the noise in
detection.
photo detection.
So
So
suppose
suppose
IT
IT
is equals to
is equals to I
plus
plus
delta
delta
delta IT,
delta IT, or you can write
IT.
delta IT.
Okay.
Okay.
So these are
So
the
these are the
fluctuations.
fluctuations.
So you can represent it
Represent it
like this.
like this.
So you
So
have
you have
this is your mean,
this is your mean current.
this is your time,
This is your time,
and
and
so the dotted
so the
line
dotted line is
represents
representing your
value of
mean value of current,
top
and
of
on
it
the top of that there are some
which
fluctuations
are
which
represented
are
by.
represented by the delta IT.
So the
So
current
the current generated.
the current
The
generated
current generated
from the photo
from the photo detector
photo detected
photo
delta I,
detector delta I,
which is also
which
from,
is also a function of time,
because we saw that
because we saw that
with time
with time
the fluctuations
the
are changing.
fluctuations are changing.
So the
So the
fluctuations are
fluctuations are
a function of
a
time.
function of time.
So now,
So now,
if we want to
if we
define
want
the
to define the
noise power,
noise
that is
power,
P
that is
noise,
P noise,
we are not
we are not uh,
doing the
doing
derivation
the
part here.
derivation part here.
You are just
You are
writing the
just writing the
expression here.
expression here.
That is
That is
P noise is
P
equals
noise
to
is equals to
delta I
delta
square
I
RL
square RL
is equivalent
is equivalent to 2
to electronic
into
charge
electronic
into the
charge
delta
into the
F, that
delta
is the
F, that is the
bandwidth,
bandwidth,
and RL, that
and
is the
RL,
load
that is the load
resistance.
resistance.
So here
So here
we have this
we
plot.
have this plot.
So
So
this is the class,
this is the classical noise,
and
and
this is the short
this is
noise,
the short noise level.
short noise level,
Short noise level,
and this is
and
defined
this is defined by
P
P
noise,
noise,
that is noise
that is
power
noise power as a function of frequency.
Okay.
Okay.
In the low
So in the
frequency,
low frequency region,
we have high
we have
noise.
high noise. You can see that.
P noise
P noise
function
as a function of frequency
1 by 2.
1 by tau d.
So in the low
So in
frequency,
the low
we
frequency
have
region,
high
we have
noise,
high
which is
noise,
because
which
of
is
the
because of the
thermal and
and
vibrations,
vibrations,
which is because of
which is because of the
higher
at higher
frequencies.
frequencies.
At higher
At
frequencies,
higher frequencies, vibrations and temperature variation offer for a more time.
and they will not
Will not
contribute.
contribute.
At higher
At
frequency,
higher
we have
frequency,
the
we
short.
have the short noise.
This is my
This is my
classical noise.
classical noise.
Okay. What is short
What does
noise mean?
short noise
The
mean?
short
The
noise
short
means
noise means
photons are incident.
photons are incident and
Some current is
some
produced
current is
and that will
produced and
create
that will
noise.
create
And it
noise,
is
and it is
essentially
essentially
short noise is
short noise is
essentially a
essentially a
signature of
signature of
intrinsic
intrinsic
statistics.
statistics.
Intrinsic
Intrinsic
statistics
statistics
that are present
that are
inside
present
this.
inside the system.
Okay.
Okay.
So
So, and
why are we
why are
interested
we
in
interested
measuring
in
the short?
measuring the short noise?
So measurement
So,
of short
measurement
noise
of
will
short
give
noise will give
measurement of
measurement
short
of
noise
short noise
will give
will give
insight
insight of
photon
photon
statistics.
statistics.
So
So,
what does this
what does this
spectrum
noise
tell
spectrum
you?
is
So when
telling you?
there
So,
is
when
low
there is low
frequency,
frequency, in the low frequency region,
it is
it
dominated
is
by the
dominated by
classical
the
noise
classical
1 by
noise
f.
1 by f.
In higher
In higher
frequency, there
frequency,
is short
there is
noise,
short noise
Poissonian
and Poissonian
statistics of
statistics
detection,
of detection,
and beyond
and
this,
this,
beyond the detector
beyond the
response,
detector
that is 1
response,
by
that is
2.
1 by tau d.
After that,
After
if
that,
any
if
current
any
is
if
after
after
any photon is
any
coming to
photon
the
is coming to
detector,
the
there is
detector, there
no
is
response.
no
So
response.
basically, the
So
short noise
basically, the short
measurement will
noise
give the
measurement will
direct
give the
info on
direct
the
info
photon
on the photon
statistics.
statistics.
So now let's
So
take
now
a 10
let's take
minutes
a
break,
10 minutes
and after
break,
that we
and after
will
that we
resume
will
and we will
resume
solve
and we will
the
solve the
example.
example.
Okay, let's start the
Start the
example. So
example. So
we have
we have
read about
read about the
average photocurrent
average photocurrent
efficiency
quantum
of the
efficiency of
detector
the detector
and what will be the
and what
current
will be the current
fluctuations.
fluctuations.
So
So
suppose we have
we have
a helium
a
neon
helium neon laser
with power
with power
6th
sixth
power
with
10
power
milliwatt
10 milliwatt
and
and
lambda is
lambda is
632
632.8 nanometer.
and
And
responsivity is
responsivity is
0.43,
0.43.
and RL
And
is,
RL is,
that is load
that is
resistance.
load resistance, is given by 50.
So we want
So
to
we want to
calculate
calculate
first of all the
first of all the
efficiency.
quantum efficiency.
The
The
first
first
question is
question.
quantum
Quantum
efficiency of
efficiency of
detector.
detector.
Eta.
Eta.
So
So
responsivity is
responsivity
given by
is
R
given
is
by
equals
R
to
is
eta
equals
E
to eta E
upon H
upon
plus
H
omega.
cross omega.
It is
It
equivalent
is
to
equivalent to
0.43.
0.43.
So we can
So
calculate
we can calculate the
is
E
equals to
is equals to 1.2
by
by
0.632, which is
0.632, which is
equivalent to
equivalent to
1.9 electron.
1.9 electron volt.
So
So
eta equals to
eta equals to
0.43
0.43
by
by
E is the
E is the
electronic charge
electronic charge
and H cross
and H
omega
cross omega 1.9.
So
So
eta is equals
eta
to
is equals to
0.43
0.43 into
1.9,
1.9,
which is
which
equivalent
is
to
equivalent to
4%.
84.4%.
So this
So
is
this
the
is your
quantum
quantum
efficiency
efficiency
of detector.
of detector.
Now
Now,
E part
key
is
part is
we want to
we
find
want
out
to find
the
out the
average.
average photocurrent,
Which is given
which
like
is
this.
given like this.
So average
So
photocurrent
average
is
photocurrent
responsivity
responsivity
multiplied by
multiplied
power.
by power.
So which is
So which is
0.43 into
0.43
10
into 10
milliwatt. That is
milliwatt. That is
4.3.
4.3 milliampere.
Now C part
Key
is
part
we want to
and
find out the
find
current
out the current
fluctuations
fluctuations
within
within
bandwidth.
bandwidth of,
Bandwidth
so bandwidth, because we know that
by
we
delta
require delta F
within bandwidth
within
of
bandwidth
100
of
kilo.
100 kilohertz.
Okay.
Okay.
So
So
this
that is
delta
delta I square
is given
is given by
2E
2E
delta F
delta F
I
I
is equals
is
to
equals to
2 into
2 into
1.6 into
1.6
10
into
raised to
10
power
raised to
minus
power minus 90
into
into
10 raised to
10 raised to
5.
power 5.
That is 100
That is
kilowatt. That
100
is 10
kilohertz.
raised to
That is
power
10
5
raised to power
first.
5 first.
And I is
And I is
4.3
4.3 milliampere. That is
4.3 into
4.3 into
10
10 raised to power minus 3.
so that
So
is
that is,
so delta
so
I
delta I
will be the under
will be the
root of
under root of
2E delta
2E
F.
delta F I.
So which will
So
give
which
you
will give
12
you 12
nanoampere after
nanoampere
plugging
after
the
plugging in the
values of all
values
these
of all these
constants.
constants.
And
And
that is the 12.
That is the 12 nanoampere.
And the next
And the next is
noise power
noise power
in dB.
in dB.
After
After
amplification with
amplification with
power gain of
power gain of
20
20
decibels.
decibels.
So
So
power noise
power
is given
noise is
by
given by
delta I
delta I square
into RL,
into RL,
which will give us
which
the
will give
10
us
raised
the
to
10
power
raised to
minus
power
15
minus 15
volt. And
volt.
after
And after
amplification,
amplification,
so it is a
so it
10
is
raised to
a
power
10 raised to power minus
10,
2.
10
So
raised to power 2,
10 raised
10
to power
raised to
2,
power
10
minus
raised to power
13
minus
volt,
13 watt,
which is equals
which
to
is equals
minus
to minus
100 dB.
100 dB.
So,
So,
so we saw
so
that
we saw that
loss
loss
will always
will
push the
always
photon
push the photon
statistics towards the
statistics towards
classical
the classical, that is Poissonian or super Poissonian.
and Poissonian
And
detection
Poissonian
can come
detection
from
can come
classical
from
fields to
classical fields
prove
too, not
the
proof of the
quantumness.
quantumness.
Sub-Poissonian
Sub-Poissonian
statistics
statistics
or noise below
or noise
short
below
noise
short
equals to
noises
definitive
equals to definitive
evidence of the
evidence of
quantum
the
field.
quantum light.
Then
Then
how can we
how
reduce
can we
the
reduce
noise?
the noise?
So either we
So
can
either
work
we can
at
work
higher
at
frequencies that
higher
is avoid
frequency,
the
that is
classical
avoid the
noise,
classical noise,
or
or
we can
we can
or we can
or we can
work with the
work with
balanced
the balanced
detection. What does
detection.
this mean?
What does this mean?
In this
In
case,
this case,
we have
we have
we will split
we
the
will
beam by
split the
using the
beam by using the
50-50 beam
50-50
filter.
beam splitter.
So one
So
portion of
one
the light
portion of
is
the light is
reflected and the other
reflected
one
and
is
the other one is
transmitted.
transmitted.
So and we will
So and we
use
will
it
use
will pass
and
through
it
the
will
PD1
pass through the
photodiode
PD1
1
photodiode
and
1
photodiode
and
2,
photodiode 2.
and
And
then at the
then
detector
at the
we will
detector
measure
we
the
will measure the
difference of
difference
I1
of I1
minus I2.
minus I2.
So we
So
know that the
we know
classical
that the
noise will
classical
be
noise
common in
will be
both the
common in
cases,
both the cases,
like because of
like
the
because of
thermal,
the thermal,
like temperature
like
variations or
temperature
any
variations or any
vibration that will be
vibration, that will be
same
same
in both the
in both
cases
the
of PD1
cases of
and
PD1
PD2.
and PD2.
So if we
So
measure
if we
the
measure
I1
the
minus
I1
I2,
minus I2,
that will
that will
cancel the common
cancel
mode
the
noise
common
or
mode
classical
noise or
noise, and
classical
it will
noise,
leave
and it will
only
leave
short noise that is
short
the
noise, that is the
intrinsical part.
intrinsical part.
So
So
using this
using
we
this
can
we can
detect the
detect
quantum
the quantum
statistics.
statistics.
So if the
So
current
if the current
fluctuations will
fluctuations
fall
will fall
below the short
below
noise
the
limit,
short
it
noise limit,
indicates the
it indicates the
sub-Poissonian light.
sub-Poissonian light.
So for
So,
example,
for example,
LEDs powered by
LEDs powered by
instead of
battery instead
noisy
of
AC
noisy
supply can
AC supply
generate
can
a
generate
measurable
a measurable
sub-Poissonian emission
sub-Poissonian
under certain
emission under certain
conditions.
conditions.
So
So
now
now what is
what is the
what is
concept
the
of
concept of
coherence?
coherence?
So
So,
infinite sine wave
infinite
is a
sine wave is
perfectly
a
coherent
perfectly
wave
coherent
if the
wave, and if
amplitude
the
and phase at
amplitude and
one
phase
point
at one point
in
in
space-time are known,
space-time are known,
then it is
then it
coherent
is
and we can
coherence, and we
predict
can predict
the amplitude
the
and phase
amplitude and phase
at any
at
random
any
point.
random
We
point.
can predict
We can predict
everywhere in the
everywhere in the
parametrics. In
parametrics,
the
in the
space,
space.
real sources are
Real
never
sources are
perfectly
never
coherent.
perfectly coherent.
There are two types
There
of
are two types
coherence.
of
One is
coherence. One
temporal
is
coherence
temporal
and the other
coherence,
one is
and the other one
partial
is
coherence.
partial coherence.
So
So
Then what is
within
temporal
what is
coherence?
temporal
Within a
coherence?
limited
Within a
coherence
limited
time
coherence time
that is defined by
that is defined by
tau c, the
tau
phase
c, the
relation is
phase relation
conserved.
is conserved.
And beyond tau
And
c,
beyond
tau c,
tau
the
c,
random
the random
can't
we
determine
can't determine
the phase.
the phase
Up to the
up to the
coherence time,
coherence
if
time.
we want
If we
to
want
detect
to
the phase,
detect the phase,
we can
we
tell.
can tell. But
Beyond tau
beyond
c,
tau
there
c,
is
there is
unpredictability
unpredictability
in the phase
in
because
the
there will
phase
be
because there will
random
be a random
variables.
phase jumps.
And the temporal
And the temporal
coherence is
coherence
related
is
to the line
related to
width.
the line width.
So narrow
So
line width
narrow line
laser
width laser
implies the
implies the long coherence time,
whereas the broad
whereas the
line
broad line width,
that is a white
that is
light
the white light,
and the
it
short
represents the
coherence
short
time.
coherence time.
In this case, you
In
can
this
see
case,
that
you can see that
if we have
if we
this
have this
in the portion
in the
A,
portion A,
if we want
if we
to
want
detect the
to
phase at
detect the
this
phase at this point,
if we want to
if we
detect
want to
the phase
detect
at this
phase
point
at
or
this
this
point
point,
or
we
this
can
point,
easily
we can easily tell.
but after
But
this phase
after this
jump
phase jumps,
after this phase
after
jump
this
we
phase
cannot
jump, we
detect the
cannot
phase
detect the phase
at this point
at
because
this point because there is
it is beyond
it is
toss.
beyond the tossing.
Similarly, for the
Similarly, for
specially,
the
if we want
specially,
to
if we
calculate
want
the
to calculate the
phase at this
phase
point
at
and
this
at this
point
point,
and at
it
this
is
point, it is
easy to
easy to
tell.
tell.
But beyond this
But
point,
beyond this point,
we won't be able
we
to
won't
tell
be able
this.
to tell this.
So similarly, the
So
special
similarly, the special
coherence is
coherence
within a
is
coherence
within a
length.
coherence
Different
length.
spatial
Different
points have
spatial
fixed
points have
relation,
fixed relation,
and beyond
and
LC,
beyond LC,
that
the
relation is
that
lost
relation is lost and due to
multiple
because of
wave
multiple wave
contribution.
contribution.
So, for
So,
example,
for example,
we measure the
we
stars
measure the
using
stars using
interferometry that
interferometry that
Michelson or
Michelson or
uh,
uh,
initially it
initially
was
it were measured using
Michelson
Michelson
and
interferometer
later
and
Henry
later
Brown
Henry
SPT
Brown
method.
SPT method.
So
So
SPT
HPT
interferometer is
interferometer is a
classical
classical
Michelson
Michelson
interferometer that
interferometer
uses
that uses
lenses and mirrors
lenses
to
and
create
mirrors to
fringes.
create fringes.
And
And
but what
but what
is the
is the
improvement?
improvement?
Like in
Like
spite
in
of
spite of
lenses or mirrors,
lenses
we
or
use a
mirrors, we
beam
use a
splitter.
beam
That
splitter.
is, we are
That is,
sending
we
the
are sending
transmitted beam to
transmitted
detector
beam to
one
detector one
and the reflected
and
beam
the
to
reflected
detector
beam to
two,
detector two,
and then we will
and
measure
then
the
we will measure the
intensity
intensity
correlations
correlations instead of
interference fringes,
interference fringes,
and we will
and
add
we will
delay
add delay
electronically or
electronically
specially
or
in the
specially
original.
in the original.
So
So
suppose what is the
suppose what is the
mathematical intensity
mathematical
on the
intensity
detector
on the
is given
detector
by
is given
IT
by
is equals
IT
to
is equals to
I plus
I
delta
plus
IT. That
delta
is
IT,
mean
that
value
is
of
mean
current
value
and
of
the
current and the
fluctuations regarding
fluctuations
this.
regarding this.
So
So
so DC,
DC,
so only the
so only the
fluctuations.
fluctuations
DC will be
DC
blocked
will
and
be
only
blocked,
the
and only
because there is a
the because there is a
capacitor
capacitor
diagram,
in the diagram,
and the only the
and the only the
fluctuation
fluctuation
delta
delta
IT will
IT will be
contribute. So
contribute.
HBT
So HBT
output current will be
output current will
proportional
be
to the
proportional to the
del IT.
del IT
Del I
del I
proportional to
HBT
the average
proportional to the average value product of
fluctuations at
fluctuations
time t
at
and the
time t and the
fluctuations at
fluctuations
time
at
t
time
plus tau.
t.
So if
So
we consider the
we
case
consider
tau is
case
equals to
tau is
0,
equals to
it
0,
will be
it will
proportional
be
to the
proportional to the
IT
IT
delta I
delta
to the
I
whole
t
square
का whole
average
square
value.
का average value.
That will be
That
always
will be always
positive and the
positive and the
fluctuations will be
fluctuations will
squared.
be squared.
When the tau is
When the
greater
tau is
than the
greater than
coherence
the
time,
coherence time,
the
the
fluctuations will be
fluctuations will be
uncorrelated and the
uncorrelated
average
and the average
product will
product will
tend to 0.
tend to zero.
So this was
So
the
this
case
was the case
where
where
we are having
we
the
are having the
435.8 nanometer
435.8
light from
nanometer
the
light from the
mercury lamp.
mercury lamp.
It is passing.
It is passing.
It is going to
It
the
is going to
beam
the
splitter.
beam splitter.
One part is
One part is
transmitted, another one
transmitted,
is
another one is
reflected. It
reflected.
is going
It
on
is
to the
going on to the
photomultiplier tube where the
photomultiplier tube where the photo
current will be
current will
generated,
be generated,
and
and
then there is
then
AC
there is
coupled
AC coupled
amplifier which
amplifier
generates
which
the
will
delta
generate the
I2 which is
delta I2, which
proportional to
is
the
proportional to the
fluctuations,
fluctuations,
and
and
then there is a
then there is a delay generator.
so
So
then
then
IHBT will be
IHBT
proportional
will
to
be
the
proportional to
average
the average
value of product of
value of
delta
product of
IT and
delta
the
IT and the
fluctuations produced.
fluctuations produced.
So if tau is
So
equal
if
to
tau is equal to 0, we can see that
it will be
it will
proportional
be
to this one,
proportional to this one.
and the
And the
the
multiplier,
output of
the
this
output of this
HPT is given by
HPT is
this.
given by this.
So now the
So
second
now
order
the second order
correlation.
correlation function G2.
So what is the definition?
What is the
So tau
definition?
is
G2
defined
tau is defined
for
for
monochromatic light wave,
monochromatic
which is
light
defined
wave. It
by
is
I.
defined by I.
The current at
The
time,
current at time, the intensity at time t, intensity at
plus
time
tau
t plus tau
upon the average
upon
value
the
of the
average
product
value,
of
the
these
product
the
of these, and
individual
the
averages
individual
of
averages of
IT
IT
and IT plus
and
tau.
IT plus
So
tau.
for the
So
large
for the large
time,
coherence time,
G2 at
G2
tau
at tau
tends to 1,
tends to 1,
and at
and
tau
at
is equal to
tau is
0,
equal to 0,
it will be
it will
coherent
be
laser where
coherent
there are
laser
no
where there are no
fluctuation.
fluctuation.
That is at tau is
That
equal
is
to
at tau
0,
is equal to 0, G2 0 is equals to 1.
and when there will
And
be
when there will be
thermal or
thermal
chaotic
or
light,
chaotic
there
light,
will
that
be
where
strong
will be
bunching.
strong bunching,
G2 is
G2
greater than
is
1.
greater than 1.
So now
So now
let's solve one
let's
example.
solve one example
We want to
that
find
we
out
want to
G2
find out
for
G2 0 for
monochromatic light wave,
monochromatic light wave,
where
where
IT
IT
is equals to
is
I
equals to
naught
I naught
1 plus
1
A
plus A
sin omega
sin
t
omega t
with
with
A modulus
A
is
modulus is lesser than 1.
lesser than 1 equal.
Lesser than or
So
equal to.
G2
So
is
G2 is
equals to
equals to IT
IT plus
IT
tau.
plus tau.
So since
So since
tau is equals to
tau is
0, so
equals to 0, so
IT will
IT
give you
which
I
will give
naught
you I naught
square
square
1 plus
1
A
plus
sin
A
omega
sin omega
t square
t square
upon
upon
I square.
I square will be I naught
Square.
square only.
So I naught
So
square
I naught square will I naught square
cancel.
will
Now we
cancel.
want to
Now
find
we
out
want to
1
find
plus
out
A
1 plus
square
A square
sin square
sin
omega
square omega t
plus 2
plus
A
2A
sin omega t.
sin.
It will give
It
you
will give you
1 plus
1
A
plus
square.
A square.
Then we
Then
can write the
we
sin
can
square.
write the sin square. So
The average
the
value
average
of
value of
omega t
sin
is 0.
omega t is 0.
And we can
And
write
we can
the
write
sin
the
square omega
sin
t
square
is
omega
1
t is 1
minus
minus
1
1
minus
minus
2 cos
2
omega
cos
t
omega t
by 2.
by 2.
So it will give
So
us
it
the
will
1
give us the
plus
1
A
plus
square
A square
by 2 at
by 2
1
at
equals
2
to
is
0.
equals to 0.
So G2 to
So
we know
G2
the
to we know
general
the
value
general
of.
one.
So now
So now
which so
it,
that
so
the
that
G2
the
is the
G2
second order
is the second
correlation
order
function, is
correlation
a
function,
powerful
is a
tool to
powerful tool
characterize
to
the light
characterize the light
characteristic. If it is
characteristic.
equals to
If it
1,
is equals to 1,
that's a coherent
that's a
light.
coherent
If
light.
it is a
If it
thermal
is a
light,
thermal light,
the
then it
value
is
is
the
2,
value is 2,
like greater than
like
1,
greater than
G2 0
1,
is equals
G2
to
0 is
2.
equals to 2.
And if it is
And
at the
if it is
quantum
at the
single photon
quantum
light
single
source,
photon light source,
in that case,
in that
it
case,
will be lesser
it
than
will
1.
be lesser
So
than
we
1.
will
So
talk
we will
about this
talk
in the
about this in the
next lecture.
next lecture.
And it is
And
used
it
to
is
measure
used to
the
measure
coherence
the
time,
coherence
coherence
time,
length, and we
coherence
can
length, and we
classify
can
light as
classify
coherent,
light as
thermal, or
coherent,
quantum
thermal, or
basis of the
quantum
G2
basis of the
values.
G2 values.
Next,
Next, coming to the assignment.
so photon
So photon
statistics.
statistics.
So the first
So
question
the
is
first
photon
question is
statistics
photon
of light.
statistics of the light.
Describe the
Describe
fluctuations
the
in electric
fluctuations in
field,
electric
photon
field,
quantum
photon
efficiency of
quantum
the
efficiency of the
photodetector,
photodetector,
the fluctuation
the
in the photon
fluctuation in the
number.
photon
So
number.
in
So
case of
in
photon
case of photon
statistics, we are
statistics,
dealing
we
with
are
the
dealing with the
fluctuations in the photon
fluctuations in the
number per
photon
unit
number per
interval.
unit interval.
Per unit
Per unit
interval. So the
interval. So
correct
the
answer is
correct
option
answer
3.
is option 3.
In Poissonian
In
light, the
Poissonian
standard
light, the
deviation of
standard
the
deviation
photon
of
number
the
around
photon number around a mean value is given by
so we saw that delta
that
n
delta n
is equals to
is
under
equals
root
to
of n
under root
bar.
of n bar.
So this is
So
your
this is your
n bar is
n
equals
bar
to
is
mean
equals to
value,
mean value,
and the delta
and the
is
delta n was
deviation.
standard deviation.
So
So
now consider a
now
beam of
consider a
light
beam of
photon
light
energy
photon
2
energy
electron
2
volt with
electron
an
volt with
average
an
power of
average power of 1
so
nanovolt.
we want to
So we
calculate
want to
the
calculate
average
the
photon
average
flux
photon
phi
flux
is
phi is
so
2.
we have E
We have
equal
E is equals
2 electron
to
volt,
2 electron volt.
average power is
Average
1
power is 1 millivolt.
APH is equal
APH is
to
equals to.
so we want to
So we
find
want to
phi
find phi
is
is equals
P
to P
upon energy of
upon energy of photon
1 into 10
1
to the
into
power
10 raised to
minus
power
9,
minus 9,
3.2 into 10
3.2
to the
into
power
10 raised
minus
to power
9.
minus.
So 1 into
So 1 into 1 by
3.2 is equal
3.2 is equals to.
to
So,
so 1 upon
so 1 upon 3.2 will be.
so it will give you
It will give you
3.125 into 10 is to the power
3.125 into 10 is to power
photons
9
per second. So you want to
photons per
calculate the photon
second. So we
flux.
want to calculate the photon flux only.
Next question is
Next
the
question is
count time of
a count
1
time of
nanosecond
1
will contain an
nanosecond will
average.
contain an
So here we
average.
are given that delta t is equals to 1 nanosecond and we are asked the n. N is
Second,
equals
and
to
we are
5
asked the
into
n.
delta t. So
N
we
is equals to
calculated
5 into delta t. So we calculated 5.
3.125 into 10 is to power minus 9
3.125 into 10 is to power minus 9
into 10 is to
into
power
10 is
minus
to power minus
3.125
3.15
photons on
photons
average.
on average.
Next the question
Next,
5
the
is
question 5
a
is
segment of
a
the
segment
beam
of the
with a
beam
length of
with a
3
length of
meters
3 meter
correspond to the count
correspond to
time.
the count timer.
So
So
we want to
we want
calculate
to
the time
calculate the time
corresponding to
corresponding to
3 meter beam
3
segment.
meter beam segment.
So T is
So
equals
T is
to
equals
L
to
by C,
L by C.
that is 3
That is
meter
3 meter
by 3 into
by
10
3 into 10 raised
8
to power
meters
8
per second,
meters per second,
which is 10
which
to
is
the power
10 raised to
minus
power
8
minus
second or
8
10
second or 10
nanoseconds. So the correct
nanoseconds. So the
answer is
correct answer is
last option.
last option.
Next question.
Next question.
A beam segment
A
of
beam
3
segment
meter
of
will
3
contain
meter will
average number of
number
photons.
of
So average
photons. So
number of
average number
photons
of photons
again and is
again
equals to
and is
phi
equals
t.
to phi
So
t.
phi is equals to 3.125 into 10 raised to
So
power
phi is equals to 3.125 into
9
10 raised to power
and t
9
10 raised to power minus 8.
and t
So that
10
is
raised to power minus 8.
31.25.
So that is 31.25. So the option is
The fifth option is
the
the
fifth
correct
option is
option.
the correct option.
Next is
Next
photon
is photon
statistics. A
statistics for a
coherent light
coherent light
with
wave
constant
with constant
intensity is given
intensity
by
is given by
sub-Poissonian,
sub-Poissonian,
super-Poissonian,
super-Poissonian,
Poissonian,
Poissonian,
Gaussian,
Gaussian,
Lorentzian, or
Lorentzian,
binomial.
or
So we
binomial.
saw that
So we
if
saw
we
that
are
if we are
talking about the
talking
coherent
about the
light wave,
coherent light wave,
then it is given
then it
by
is
the
given by the
Poissonian
Poissonian
distribution.
distribution.
A delta
A delta
is
n is
to
equals to
10 bar.
10.
Next question.
Next
The
question
figure
is the
below
figure
depicts the
below depicts the
Poisson
Poisson
distribution for mean
distribution for
values.
mean values.
N bar of
N bar of
1,
1,
1, 5, and
1,
10.
5,
And we have to
1.
answer the following question. So in the first
The
graph, it
first
is
graph, it is
N bar is
for
equals
n
to
bar is
point
equals
1.
to 0.1.
So
So
probability
probability
distribution
distribution
is P of
is
N
P of
is
n
equals
is
to
equals to
N bar
n bar n
and factorial.
and factorial.
The probable
The
value
probable value
is
is
N bar. So
n
peak
bar.
is
So
it
peak
at
is it at.
so the probability
So the
distribution
probability
has a peak
distribution has a
has
peak
it
has it.
the probability
The probability
distribution has a
distribution
peak
has a
is it
peak
at N
is
bar.
it at n bar.
The correct option
The
is
correct option is second option.
with
with
increasing
increasing
relative
n the
size
relative size
fluctuations in the
fluctuations
photon
in the
flux.
photon flux.
So standard deviation,
Standard deviation,
we know
so
that
we know that relative
fluctuations
fluctuations
is given by
is given by
sigma by n.
sigma by n.
Sigma is
Sigma
under
is
root n
under root n,
and n
and
is
n is
n bar which is
n
equals to
bar,
1
which is
by
equals
root
to 1 by root
n. It
n.
is asking us
It is asking us with increasing n bar.
with
So
increasing the
with
mean
increasing
value,
the mean value,
the relative
the
size of
relative size
fluctuation
of
will
fluctuation
decrease.
will decrease.
So the
So
fluctuation
the
will decrease.
fluctuation will decrease.
Now match the
Now
types of
match the
light
types
with
of
its
light with its
corresponding photon number
corresponding photon number
distribution. So
distribution.
Poissonian,
Sub-Poissonian,
and super
Poissonian, and
Poissonian.
super
So
Poissonian.
we know that
So we know that
for
for
sub-Poissonian, delta
sub-Poissonian,
n
delta n
is lesser
is
than
lesser
n bar
than n bar
mean value.
mean value.
For
For
Poissonian,
Poissonian, delta n
under
is
root
equals
of
to under root
mean
of
value,
mean value,
and for super
and for
Poissonian,
super
delta n
Poissonian, delta
is
n
greater
is
than.
greater than.
So which option
So
is
which
this?
option is this?
A will match
A
to
will match to second,
delta n
delta n
1
to 1,
and C3.
and C3.
So the first
So
option
the
is
first
correct.
option is correct.
Next is choose the
Next is choose the
detectors that
detectors
are typically
that are
used for
typically
single
used for
photon
single
detection.
photon detection.
So,
So,
so we saw
so
that
we
we
saw
are
that
using
we are using
the
the
SPAD,
SPAD,
photomultiplier tube,
photomultiplier tube,
silicon
silicon
photodiode,
photodiode,
phototransistor,
phototransistor,
photoconductive detector,
photoconductive detector,
or the
or the
this
this
biometric
biometric
bolometric
bolometric
photodetector. So
photodetector.
in
So
SPAD,
in SPAD,
SPAD is single
SPAD is single
photon
photon
avalanche diode.
avalanche diode.
So
So
it works
it
in
works in
Geiger mode.
Geiger mode.
That is a single
That is a
absorb
single
photon
absorbed photon will
will
trigger a
self-sustaining
self-sustaining
avalanche and will
avalanche,
produce
and
a
it will
large,
produce a large
easily
and
measurable
easily
pulse.
measurable
So
pulse.
high
So
detection
high detection
efficiency and
efficiency and
excellent timing.
excellent timing.
So we use
So we use
the silicon
the
SPAD
silicon
for
SPAD
visible
for
reason
visible
and the
reason, and the indium
and
InGaAs
SPADs for
and
telecom.
SPADs for telecom.
Then
Then
PMT, so it's a
PMT, so
photo
it's a
multiplier
photo multiplier tube. So here a
photocathode.
photocathode
Emits a single
emits a
photon.
single photon,
Emits a single
emits a single photoelectron,
photoelectron which is
photoelectron, and which is
multiplied through a
multiplied
dynode
through a dynode chain
to a large
to a
current
large
pulse.
current
So
pulse.
it will give
So
a
it will
very
give a
high
very
gain
high
and
gain
single
and
photon
single photon
sensitivity. So it is
sensitivity.
very
So it is
common in
very
low light
common in low
experiment.
light experiment.
So we use
So we
these
use these
two things
two things
as
to
detectors.
as detectors.
The others
The
are
others
silicon
are silicon
photodiodes, which
photodiodes. So
generates
it
very
generates
tiny
very
current per
tiny
photon
current per photon,
and is used for
and is
analog
used
light
for analog
detection,
light
not for
detection,
single
not for
photon,
single photon,
because it doesn't
because it
resolve the
doesn't
additional
resolve the
noise
additional noise
amplification.
amplification.
And for
And for
phototransistor,
phototransistor or
photoconductor detector,
photoconductive
we
detector,
have
we
gain
have
but much higher noise and generally too insensitive for
for
single photon counting. And the last is
single photon
bolometric
counting.
photodetector.
And the last is bolometric
These measure the
photodetector.
heating from many photons,
These
not
measure the
single
heating
photon.
from many photons, not
So
single photon.
these are for the
So
specialized
these are
cryogenic
for the specialized cryogenic
bolometers. So the
bolometers.
correct option is
So the correct
SPAD
option is
and PMT.
SPAD and
The
PMT.
next question
The
is
next
match the
question is
photon
match the
statistic with
photon
its
statistic with
corresponding
its
classical
corresponding
equivalent.
classical equivalent.
So the
So
super Poissonian
super
is
Poissonian is
non-classical light. So
non-classical
the
light.
A
So
is
the
1.
A is 1.
So super
So
Poissonian
super
is
Poissonian
partially
is
coherent,
partially coherent,
chaotic,
chaotic,
incoherent, or
incoherent,
thermalite.
or
So A is
thermalite. So A
second.
is second.
Poissonian is
Poissonian is
perfectly coherent
perfectly
light.
coherent light.
Third
The
and sub
third, and
Poissonian
sub
is none.
Poissonian is none.
So A
So A
second,
second,
B third,
B
C
third,
first.
C first.
Last option.
Last option.
The
The
Next question is
Next
in
question
regard
is
to
in
a
regard to
photo
a
detection
photo
process
detection
are in the
process are
following
in the
sequence of
following
events
sequence of events chronologically.
So E1
So
is
E1 is
triggering and
saying
release of
triggering and
more
release of more
electrons.
electrons.
E2 is generation
E2
of
is
a current
generation of a
pulse,
current
interaction
pulse,
of light with
interaction
the
of light
atoms in
with
the
the atoms
detector,
in the
then
detector,
liberation
then
of.
liberation of.
So we saw
So
that
we saw that
first of all the
first of
light
all
will
the light will
incident.
incident,
So
so
illumination by light
illumination
beam.
by light beam,
Then
then
interaction.
interaction.
The light will
The
interact
light
with
will
the
interact
atoms
with
in
the
the
atoms in
detector.
the detector.
That is first
That is first
E5,
E5,
then
then
E3,
E3,
and
and
then there will
then
be
there will be
generation of
generation of
individual electrons
individual
by the
electrons by the
photoelectric effect.
photoelectric effect.
That is option
That is option
E4, that is
E4,
liberation
that
of
is liberation
individual
of
electrons by
individual
the
electrons by the
photoelectric effect.
photoelectric effect.
Then
Then
there will be
there will
triggering
be
and the
triggering
release of
and the
more
release of
electrons,
more
that is
electrons, that
E1,
is
and
E1,
it will
and it
generate
will generate
a current.
a current pulse.
So
So
last option is
last option is
E5,
true.
E3,
E5,
E4,
E3,
E1,
E4,
E2.
E1, E2.
The last question
The last
is a
question
10
is a
milliwatt
10
telephone
milliwatt
laser
telephone
operating
laser
at a
operating
wavelength
at the wavelength
632.8
632.8
nanometers
nanometer is incident
on a
on a
photodiode with a
photodiode with a
responsivity of
responsivity of
0.43,
0.43,
and we want to
and we want
calculate
to
the
calculate the
efficiency of
efficiency of
the detector.
the detector.
So
So
E,
E,
so lambda
so
is
lambda is
632.8
632.8
nanometer.
nanometer.
E will be
E will be
1.5
1.2 by
0.632 is equals
0.632
to
is equals to
1.9
1.9
volt.
electron volt.
Responsivity is given
Responsivity is
by
given by
eta E
eta E
by H
by
cross.
H cross omega.
So
So
it is
it is
0.43
0.43
is equals to
is equals
eta
to eta
into
into
1.6 into 10
1.6
raised to
into 10 raised to
minus
power minus 19,
and
and
H cross
H cross omega.
so
So
1.9 into
1.9 into
1.6 into 10
1.6
raised to
into 10 raised to
minus
power
19.
minus 19.
And then eta
And
is
then
equals
eta is
to
equals to,
it's
it's
already
already we did this same numerical
in the lecture
in the
also,
lecture also,
and it will give
and
you
it will give you
84.4%.
84.4%.
So how can
So
we?
how can we?
So 84%
So 84.4%
is the correct.
is the correct answer.
Okay, so
So
this was all about today.
all about today.
So we in
So we in
today's
today's
lecture we
lecture we
saw that
saw that
what are
what are
photon
photon
statistics, how can we
statistics, how can we
classify the
classify
light
the light
on the basis
on the
of
basis of
Poissonian
Poissonian
statistics,
statistics,
what is G2,
what is
second order
G2, second
correlation
order
function,
correlation
and on the
function, and
basis
on
of
the basis of
that also we
that also we can
we will
define,
measure
we will measure
experimentally.
experimentally these things.
In the next
In the
lecture we
next
will see
lecture we
that
will see that
what will be the
what
nature
will
of
be the
light
nature of light
when
when
it will when
it
the
will
G2
when
will
the
be lesser
G2 will
than
be
0.
lesser than 0.
Okay, so
Okay,
thank you.
so thank you.